Hi.
A long-haired man in a black button-down shirt. Text, Tristan Slominski, Site Reliability Engineering Manager, Indeed.
My name is Tristan Slominski, and today I will talk to you about why SLOs are useful. First, a quick overview of what a service level objective is.
Title, Service Level Objective, SLO. Table with 3 columns labeled %, noun plus verb, plus within in brackets, period. 2 rows reading, 99%, requests respond within 10 ms, 2-week rolling, 99%, requests succeed, 2-week rolling.
A service level objective consists of 3 parts. The %, the noun and verb with an optional within clause, and a period. I'm a fan of this particular table format because it highlights the relevant information without anybody having to twist words into a sentence. I can present this and all of you can make a sentence in your head, and I found most people tend to forget bits and pieces of it, like the period. You're probably used to this meaning something like a performance of the system, of reliability of the system, but I'm not attributing any meaning to it. I'm saying this is the specific artifact with this data points, and we'll worry about meaning later.
Still photo from It's Always Sunny in Philadelphia, Pepe Sylvia conspiracy theory meme. A dark-haired man with a beard stands next to a wall of printed documents, criss-crossed with red lines. He waves his hands at a second person, his eyes wide as he speaks.
Now, this presentation is going to feel a little bit like this, meaning this is what I'm going to look like to you. And it's going to feel a little bit all over the place, so I want to give you a heads up. But I promise I'm going to tie all of this together towards the end. It's an artifact that a lot of concepts here are coming from multiple disciplines that don't usually overlap.
A full moon shines in the night sky over rippling black waters.
So let's get started with an excerpt from Mark Burgess's In Search of Certainty, the Science of Our Information Infrastructure. Imagine a scene in a movie. A quiet night on the ocean on the deck of a magnificent ship, sailing dreamily into destiny. Moonlight reflects a calm pond that stretches off into the distance. Waves lap serenely against the bow of the ship, and had there been crickets on the ocean, we would have heard that reassuring purring of the night to calm the senses. The captain, replete with perfectly adjusted uniform, comes up to the night helmsman and asks, "How goes it, sailor?" To which the sailor replies, "No problem, all's quiet, sir." Making a small course correction, everything's shipshape and under control. At this moment, the soundtrack stirs, swelling into darker tones, because we know that those famous last words are a sign of trouble in any Hollywood script. At that very moment, the camera seems to dive into the helmsman's body, swimming frantically along his arteries and his bloodstream to a cavernous opening where we view a deadly parasite within him that will kill him within the hour. Then the camera pulls back out and pans out, rising above the ship, up into the air, to an altitude at which the clear, still pond on the ocean seems to freckle and soon becomes obscured by clouds. The calm sea, it turns out, is just the trough of a massive wave that miles away reaches up 10 times the height of the ship. And it's racing across the planet with imminent destruction written all over it. As we rise up and zoom out of the detail, we see the edge of a massive storm, swirling with fierce intensity and wreaking havoc on what is now a hair's breadth away on the screen. And then, pulling even farther out, just beyond the edge of the planet, is a swarm of meteorites, firing down onto the human realm, one of which is the size of Long Island. It's always Long Island, and will soon wipe out all life on Earth. Picking up speed now, the camera zooms back and we see the solar system spinning around a fiery sun, and see stars and galaxies, and we return to a calm serenity, where detail is a mere shades of color on a simple black canvas. Then the entire universe is swallowed into a black hole. Shipshape and under control.
An orange screen holds white text, scale.
So the concept that the story is intended to convey is the concept of scale.
Image of atomic structures, a sheet of hexagons formed by spheres and pipes.
Throughout this presentation, I want you to keep in mind the concept of scale. Many small components coming together to create more complex components
An image of a green molecule changes into organelles within a cell.
that create other components with defined interfaces
Pale, translucent blood cells on a gray background.
that together define many small components
The circulatory system within a hand and wrist.
that come together to create more complex components.
A man in camouflage clothing kneeling on a hillside, looking through binoculars across the gray-green valley beneath him.
With well-defined interfaces
Round huts of stone and thatch on a grassy hillside.
that come together to create components.
The image of a seaside town with low multi-story buildings and tiled roofs changes into a photo of the Empire State Building and its surroundings, to a nighttime shot of the U.S., its urban areas marked by city lights, to a world map in black and blue with pale blue arcs connecting major urban areas in different countries.
That come together to create components that combine in complex ways
Image of the Earth above the Indian subcontinent and Eastern Africa.
to create components with well-defined interfaces, etc., etc.
A blue screen with text. Things are different at different scales, yet everything matters.
And remember that while all those things are different at different scales, everything still matters. And to drive that home, think about when you have a cold. The effects that you feel at your scale of your body are caused at scales that were unknown to humans for most of human history. Everything matters at all the scales.
An orange screen with text, making sense of complexity.
So how do we make sense of all of this complexity? So one way to frame complexity is via something called the Knaven Framework. It is a sense-making framework where we discuss about our disposition towards the systems out in the world. And we can look at the world and consider systems to be ordered or unordered.
Table with two columns titled Unordered, Ordered. From bottom right beneath ordered are simple, cause with arrow pointing to effect, obvious, complicated, cause with arrow pointing to effect, requires analysis. From bottom left beneath unordered is chaotic, cause with arrow pointing to effect, no relationship, complex, cause with arrow pointing to effect, only in hindsight.
In the ordered case, we can conceive of systems that appear to be simple. And the way we'll define simple here is by the relationship between cause and effect. And for a simple system, the relationship between cause and effect is obvious. As an example, if I were to drop this clicker, it would fall down, and it would be obvious to everybody why that happened. You didn't really need to do an analysis. You would categorize it as things fall down, thing fell down. You see the cause and effect, I dropped it. Another type of ordered system that we conceive of is a complicated system. And in the framing of relationship between cause and effect, these type of systems require analysis. An example here would be a car engine, where if there's a fault in a car engine, you might have to do some analysis, see which components are failing or not, and then determine the cause of the problem. Now, another interesting bit about complicated systems, another way to kind of explain what they are is you can take them apart into pieces, and then you can then assemble pieces back together, and it will continue to work. So a car engine, an airplane, most mechanical systems function this way. On the unordered side of the systems, we can conceive of systems that appear to be chaotic. And this will define as where there's relationship between cause and effect is non-existent. There is no relationship. An example would be like I'm walking through a forest and trees start exploding. Right? It would feel very chaotic from my perspective of what is going on, and we usually wouldn't consider to analyze and think about the system. We would just act to get out of that situation. And then the other type of unordered system we can conceive of is a complex system. This one I find the most interesting, where we define the relationship between cause and effect is only knowable in hindsight. And to illustrate that, consider that if I asked you 1 year ago to conceive of all the ways of you going to end up sitting here at this talk listening to me, it would be an impossible task. But if I ask you right now and go back a year, depending on your memory, you would be able to pinpoint every decision that you've made that led you to this moment. This is an example of knowing something only in hindsight. And compared to the complicated systems, the complex systems, another way to frame it is when you take it apart into pieces, when you put it back together, it won't work. It wouldn't work for me, for example. Like me personally into pieces and putting back together.
In the center of the table appears the word disorder with a question mark beneath.
And then the other aspect of looking and making sense of the world is disorder, and this is the case where we have no idea which one of these we are in. And a lot of us spend quite a bit of time in disorder.
Text complex, cause with arrow pointing to effect, only in hindsight, complicated, cause with arrow pointing to effect, requires analysis.
So for our purposes here, let's focus on differences between complex and complicated as the way they're framed here. And this is crucial distinction to understand. So we're going to spend some time.
Across both blocks of text appears the question, why? In capital letters, angled from lower left to bottom right across the screen.
Why is it that we can predict some things in the complicated domain where we can plan things out, we can design machines, put them together, and they work, and in a complex, we can only know things in hindsight? Like, why is that?
Image of a craggy gray planet with black sky beyond.
Let's say we want to go ahead and take a picture of Pluto.
Diagram with title, New Horizons Full Trajectory, Kuiper Belt Object 2014 MU69 Flyby. Concentric ovals mark the orbits of Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. A green arc trails from Earth through Jupiter, up and to the left of the screen past Saturn and Pluto. An inset image shows the green arc turning red. The point at which green turns red is marked New Horizons, next to an orbit past Pluto of an object marked 2014 MU69, Ultima Thule Flyby. Kilometers per second, 14.43.
We'll do some math. We'll figure out which way we want to go. We'll launch a spaceship that travels for 9.5 years, 3.26 billion miles, and gets within 7,759 miles of Pluto, and we'll take some pictures.
Across the screen appears the question, how do you even? Angled from lower left to upper right.
Like, how do you even conceive of going about doing this? What condition makes such a feat possible?
A blue screen with text, the laws of physics don't change on the time scale we care about.
And a key observation to make here is that laws of physics don't change on the time scale that we care about.
Text, complex, cause with arrow pointing to effect, only in hindsight, complicated, cause with arrow pointing to effect, requires analysis, constraints, fixed at time scale under consideration.
In other words, the constraints that we are operating with remain fixed in the time scales of whatever it is that we're doing. So in the Pluto probe, that's in the time scale of physics, the laws of physics are a relevant constraint for that mission, and they didn't change. So you can probably guess the nature of constraints in a complex system.
Beneath complex, cause with arrow pointing to effect, only in hindsight, appears the text, constraints, change at time scale under consideration, due to agent actions.
And that is that constraints change under time scales that we're considering acting in. And in particular, they change due to agent actions.
Text, complex, cause with arrow pointing to effect, only in hindsight, constraints, change at time scale under consideration, due to agent actions.
So what is an example of a constraint changing due to agent action? So a pursuit of a career changes our constraints. Like, we pursue opportunities now associated with that career and not the other one. Attending this talk changed your constraints. You have to schedule things now in order to attend. If you're on call getting paged by machine, that changes your constraints. And we now need to drop whatever we're doing and resolve the issue. So almost every action we take as people changes some constraints in some way. So let's recap.
Orange screen with text, scale, complexity.
We've talked about scale and that things matter. We've talked about complexity, where cause and effect relationship is knowable only in hindsight, and where every action we take changes some constraints that we operate with. So let's now look at the effect of complexity on our ability to scale.
Blue screen with text, the Universal Scalability Law.
And we'll do that through the lens of the Universal Scalability Law. Imagine I have an item of work.
A white screen holds a blue horizontal line with white text, work.
The length of this segment represents how long it will take to execute the work.
Two vertical black lines mark the ends of the blue horizontal line. A double-headed arrow, parallel to and beneath the blue line, points to both of the black lines.
Now, let's add a worker.
A drawing of a woman appears at the left end of the blue line.
And it'll take a single worker this long to finish the work. Okay?
Two vertical black lines mark the ends of the blue horizontal line. A single-headed arrow, parallel to and beneath the blue line, points from the black line on the left to the one on the right.
Simple example.
The blue line is divided into 4 segments, each containing the word, work. Two vertical black lines mark the ends of the blue horizontal line. A single-headed arrow, parallel to and beneath the blue line, points from the black line on the left to the one on the right.
Now, let's divide this work into 4 shards, and it will still take the worker this amount of time to accomplish the work. So if we want to go faster, one thing we can do is we can divide the work.
The 4 segments are arranged in a vertical column. The top 2 each have drawings of women on the left, the bottom 2 each show drawings of men.
And now with 4 workers, we can complete the work in 1/4 of the time.
A single-headed arrow, parallel to and beneath the 4th blue line, points from the black line on the left to the one on the right.
Okay, it's a very straightforward model. There's no surprises here.
The 4 blue segments with the drawings of people appear to the left of a graph with the equation, x parentheses n equals gamma n over 1. Graph x-axis, labeled number of workers, from 0 to 15 in increments of 5. Y-axis, labeled throughput, from 0 to 15 in increments of 5. Blue line from coordinates 0, 0 to 15, 15.
So what this graph depicts is the concept of linear scalability. That is, the more workers we have, the faster we can accomplish the work. So the function x of n is the throughput given n workers. Gamma in this case is equal to 1. So we have 5 workers give us 5 throughput, 10 workers give us 10 throughput. Now our model is so far missing an aspect of what it actually takes to do work in the real world.
The 4 blue segments with the drawings of people appear alone in the middle of a white page. The drawings move slightly left to make room for orange segments on either end of the first blue segment. The lower 3 segments link to the orange segments using black lines from either end of the blue.
So the extra segments here, they represent the additional time required for distributing and integrating these work shards. We can also think of this as contention or queuing or waiting for a resource. So our first worker here has to hand out the work to the other workers, and then they have to assemble the work back together. Notice that this distribution integration adds some time to accomplish the work.
A single-headed arrow, parallel to and beneath the 4th blue line, points from the black line on the left to the one on the right.
And this line is a little bit longer than the quarter line that we had before.
The 4 blue segments with the drawings of people appear to the left of a graph with the equation, x parentheses n equals gamma n over 1 plus sigma parentheses n minus 1. Graph x-axis, labeled number of workers, from 0 to 15 in increments of 5. Y-axis, labeled throughput, from 0 to 15 in increments of 5. Blue line from coordinates 0, 0 to 15, 15. Red line arcs from 0, 0 to 15, 13.
So accounting for this contention, queuing, waiting aspect of the system, we end up with Amdahl's law. We added to the denominator of the equation the component that represents contention, sigma, and it is the fraction of the work that cannot be parallelized. So that's that first worker distributing the work and then bringing it back together. That's not the parallel piece. So even with 1% or 0.01 of the work being serialized in this manner, we start seeing the diminished throughput on the graph.
The 4 blue segments with the drawings of people appear alone in the middle of a white page. The drawings move slightly left to make room for orange segments on either end of the first blue segment. The lower three segments link to the orange segments using black lines from either end of the blue.
But waiting and queuing is not the only thing that impacts our ability to accomplish work. What happens when the workers need to start coordinating with each other?
Of the four blue segments, the second gains a short orange segment. Black arrows point back and forth to the third segment, which gains two orange segments. Black arrows point back and forth to an orange segment and a white gap in the fourth blue segment. The first segment has a white gap in between the right end of the blue line and the orange segment at the far right.
Each worker now makes other workers do extra work due to this coordination overhead. And this is bad. This is O(n) squared bad.
Text, this is bad, O parentheses n squared, bad.
In that
Three images are shown from left to right, the first with 5 blue circles, the second with 7, the third with 12. Beneath each image is n equals 5, n equals 7, n equals 12. Each point is connected to the point on either side of it and around each group. The resulting images increase in complexity from a pentagram to a kaleidoscope of lines.
Here's a visual example of O(n) squared growth. This is the nature of coherence, which is the delay for data to become consistent or coherent by virtue of point-to-point exchange of data between resources that are distributed. So we can see how much coordination we need to do with 5 workers, with 7 workers, with 12 workers.
The four blue segments with orange and white gaps appear to the left of a graph with the equation x parentheses n equals gamma n over 1 plus sigma parentheses n minus 1 plus kappa n parentheses n minus 1. Graph x-axis, labeled number of workers, from 0 to 15 in increments of 5. Y-axis, labeled throughput, from 0 to 15 in increments of 5. Blue line from coordinates 0, 0 to 15, 15. Red line arcs from 0, 0 to 15, 13. Pink line arcs from 0, 0 to 10, 5 to 15, 4.5.
So accounting for the coherence aspect of the system, we end up with the Universal Scalability Law. So we add it once again to the denominator of the equation, and the component that represents coherence, kappa, represents this percentage of work due to this crosstalk and coordination on top of contention we've done previously. With kappa set as low as 1% or 0.01, we already see the point of diminishing returns.
Black arrow at pink 10, 5.
So this graph depicts work with 1% contention and 1% coordination. And 10 workers is the point after which we get diminishing returns in that scenario. Now for context, 5 minutes of an 8-hour workday is 1%. So if your work consists of less than 5 minutes a day of coordinating and less 5 minutes a day of waiting, raise your hand.
The speaker raises his hand and looks into the audience.
Right? And I also want to highlight the range of a 2-pizza team, which typically is 7 plus or minus 5, and this is kind of where it falls on this Universal Scalability Law graph.
A black line marks the pink arc at 2, 2 and at 12, 5. A double-headed arrow joins the two black lines. Text, 2-pizza team. Across the screen appear the words, coordination kills throughput.
So what? Well, we're not going to get exact numbers out of this formulation, but what we need to take away from this is that coordination kills throughput. And it's not a lot of coordination. Just a tiny, tiny bit kills a lot of throughput. So let's recap.
Blue screen with text, scale, complexity, Universal Scalability Law.
We've talked about scale and that things are different at different scales, yet everything matters. We've talked about complexity, where cause and effect relationship is knowable only in hindsight, and where every action we take changes some constraints we operate with. And we've talked about the Universal Scalability Law, where we learned that coordination kills throughput. Okay, but isn't this supposed to be about SLOs?
Image of Futurama's Fry with squinted eyes. To the right is the question, SLOs?
So here we go. Let's build an organization as if scalability, complexity, and the Universal Scalability Law mattered, and see where the SLOs fit in. So we'll start with a solo contributor.
A drawing of a woman appears alone to the left of a graph with x-axis, labeled number of workers, from 0 to 15 in increments of 5. Y-axis, labeled throughput, from 0 to 15 in increments of 5. Blue line from coordinates 0, 0 to 15, 15. Red line arcs from 0, 0 to 15, 13. Pink line arcs from 0, 0 to 10, 5 to 15, 4.5. Black arrow on pink line at 1, 1.
The scale that we're working at is person scale, so it's single people. And the complexity is contained within one mind. Contention is limited to one person doing the work. And then the coherence is at maximum.
A second drawing, a man, appears to the right of the woman. Black arrow at 2, 2.
Now we want to get more work done, and so we're going to grow our team. The scale is still at one person. We now have 2 people. And we've introduced a complexity of one feedback loop between the 2 people to coordinate. And contention-wise, we can now do twice the work, and there's hardly any drop-off. And so the coherence is still pretty good.
3 more drawings appear to the left of the graph, bringing the total to 5. Black arrow at 5, 4.
We want to get more work done, so we grow our team to 5. The scale is still at one person scale, because we still just have 5 people working. But now the complexity is growing to 10 feedback loops. We're starting to see a drop-off. Lots of work can still happen, but now for 5 workers, we're getting 4 of throughput.
5 more drawings appear, for a total of 10. Black arrow at 10, 5.
We want to get more work done, and so we grow our team again, now to 10. And we're still thinking and looking at the person scale here. But the complexity now is up to 45 feedback loops between these 10 people. And lots of work still could happen, and we've actually increased throughput, but now we're getting to the point where after this we're going to hit diminishing returns.
Across the screen appears text, how do we grow?
So how do we grow past here? Do the obvious thing, we create teams.
The 10 drawings separate into 2 groups of 5. Black arrow marked team scale at 2, 2. Black arrow marked people scale at 5, 4. X-axis, labeled number of teams, workers, from 0 to 15 in increments of 5.
So we're going to split into 2 teams. Now the scale, notice what happens here, we start shifting the scale. We now go from a scale of persons to now to the scale of teams. Okay? And we've broken up the complexity so that each team now goes back to just having 5 people, and they have only 10 feedback loops each within the team. And so almost full 2 teams of work can happen.
Orange screen with text, let's see that again.
Now, that seems like too straightforward, so let's see this again in finer detail in slow motion. So let's visualize the feedback loops between people, which is the thing that correlates with complexity and this coherence penalty.
The group of 10 people appear to the left of the graph, each drawing with a line connecting it to the others. Black arrow on pink arc at 10, 5. 2 groups of 5 are then shown, each with a line connecting each person with the others. Black arrow at 10, 5.
When we split into the 2 teams, what happens to those feedback loops is crucial. If we do not eliminate the feedback loops when we split into the 2 teams, we haven't managed to address the coherence penalty throughout.
2 groups of 5 are then shown, each with a line connecting each person with the others in their groups. Black arrow at 5, 4.
So by eliminating these feedback loops required between teams to deliver work, we increased each team's coherence at the scale of people, right? We still have 10 people, and instead of 10 people having all the 45 feedback loops, we split them into 2 teams, and now 5 people just need 10 feedback loops because they're working together. And so notice while the arrow points from 10 to 5 people and the work throughput goes from 5 to 4, remember that we have 2 teams. So the throughput kind of heuristically here goes actually to 8. It's 2 times 4. Right? So we had still 10 people. We had throughput of 5. We went to 2 teams. Now we have throughput of 8 total. Now also I want to point out that eliminating those feedback loops between people doesn't mean like never talking to each other, right? The implication is that for our daily work, we should not coordinate with the people from the other teams. You can still be friends and talk, and that's not the type of talking I'm talking about.
2 groups of 5 are then shown, each with a line connecting each person with the others in their groups. Each group has a dotted black circle around it. Black arrow at 5, 4.
Once the teams are coherent, that allows the organization then to shift from the scale of people into the scale of teams. And now let's add that feedback loop back into the teams.
A line joins the two circles. Black arrow at 2, 2.
And here it is depicted. And so we have a feedback loop, but what is it? What does this consist of?
Black arrow labeled, what is this? To line joining circles. Question is replaced with text, API.
Well, this is an example of an API. And this is kind of why APIs are useful. So we're almost to SLOs, but first let's go through what happens when this API that I've depicted is missing, right? So notice that the way we arrived as this API between teams is that by eliminating those inter-team feedback loops between the people. And again, another name for inter-team feedback loop between people is a conversation or interaction or coordination. So if I don't have this type of API to call, or this API is inadequate, then I have to engage with another team member, say Ashley here, and I have to coordinate.
A line connects a woman in one circle to another woman in the second circle.
And we're friends and we're helpful, and so we're gonna help each other out, and then work got done. And everything's great. Now, I'm going to pause here for a second and just want to highlight that to keep in mind there are things here happening at two different scales, right? We're shifting back and forth. We have the team scale, and the communication between teams is happening at the team scale, but it's over the top of the person scale where I am talking to Ashley, right? So there are two scales at play, but they're both important. Now recall that coordination destroys throughput. And just a tiny bit of it is enough to destroy most of the benefits. So when the two of us, Ashley and I, come to an agreement, one now wants to make some changes, and Ashley points out that I'm doing a specific thing per our arrangement, so one coordinates their changes with me.
A line connects the woman in the left-hand circle to a man in the right-hand circle.
Meanwhile, Ashley became the go-to person for the thing.
A new line appears between two people in different circles.
And so I tell Brianna to talk to Ashley, and one thing leads to another, and slowly we are rebuilding this complexity that we work so hard to contain. And most importantly, we lost the benefits of the team scale that we've established, and we're now shifting the actual organizational work back down to the person scale with the coherence penalty that entails. So we can now finally explain why SLOs are useful. So let's assume we've avoided all the traps of the API inadequate, and it works great. We're communicating in the team scale, we're efficient, we have this one feedback loop between teams are coherent within each other. What happens when I make an API call and get an error response?
A black arrow marked getting points from the circle on the left to the one on the right. It is replaced with one marked nope.
Well, I have to engage with another team member, say Ashley here, to coordinate.
A line connects a person in the left circle with another in the right.
I tell Ashley that I'm getting errors, and I don't want errors, and Ashley looks into the problems and tell me that it's expected or not, and we're friends and we're helpful, and so we help each other out and work get done. And so when the two of us come to an arrangement, one now wants to make some changes, and Ashley points out that I have specific performance expectations per our arrangement. So one coordinates their changes with me.
A line connects the first person in the left with a second person in the right.
Meanwhile, Ashley became the go-to person for the thing.
A new line appears between two different people in each circle.
And so I tell Brianna to talk to Ashley, and one thing leads to another, and slowly we are rebuilding the complexity we work so hard to contain. We are shifting once again our work from the team scale to people scale, losing the scalability benefits we introduced by the teams, and this is all despite having well-defined and well-established working APIs, because we're talking about performance issues.
On the graph, a black arrow moves from the pink arc at 2, 2 to a point near 8, 4.
So, where we have an API in order to restrict inter-team coordination required between individuals regarding the functionality between teams, thus allowing our organization to shift towards the team scale, We have SLOs in order to restrict inter-team coordination required between individuals regarding the performance between the teams.
The dashed line between the two circles is marked API SLO. The black arrow moves back to 2, 2.
Thus allowing our organization to shift towards the team scale. But wait, there's more.
Text, complex, cause with arrow pointing to effect, only in hindsight, constraints, change at time scale under consideration, due to agent actions. Complicated, cause with arrow pointing to effect, requires analysis, constraints, fixed at time scale under consideration.
So recall this complex versus complicated framing. Recall that in a complicated domain, we were able to plan for the future. Whereas in the complex domain, because we know only things in hindsight and every agent action changes the constraints, we have to be in a constant feedback loop with our environment to react appropriately. We take an action, environment changes, we observe, we take an action, environment changes, we observe. So it's a constant feedback loop. And then recall relationship between the domains and the rate of change of constraints, where in a complicated domain when we're looking at something and treating it as complicated, the constraints tend to be fixed, and in complex, the constraints tend to change.
On screen are 5 circles formed by dashed lines, 3 on top and 2 below. The center circle of the 3 is connected to the other 4 circles with a single dashed line for each. The center circle and the circle on the lower right each contain 5 people, with lines connecting each person to the other. The line connecting the 2-person filled circles is marked API SLO.
When we have teams with APIs and SLOs, the APIs and SLOs serve as a way to reduce the rate of change of constraints that the teams have to deal with. So think about what a stable API and a stable SLO can offer between the teams.
Within the center circle appears the word complex.
In essence, it means that while within my team, I am dealing with the complexity of everything that is happening. I am constantly engaged in a feedback loop with my systems. I understand everything and I react constantly.
Across the 2 circles on the left side and the 2 on the right appear 2 copies of the word complicated.
I can treat all my dependencies behind API and SLO abstraction as complicated. And this is because there are people on those teams dealing with their complexity.
Within the lower right circle appears the word complex.
And they can treat all their dependents behind API and SLO abstraction as complicated.
Across the 2 circles on its left and the 2 on its top right appear 2 copies of the word complicated. Blue screen with text, SLO is a complicated container that encapsulates complexity so that at organizational scale we can accomplish more.
So this is why SLOs are useful. SLO is this complicated container that encapsulates complexity so that at an organizational scale, we can shift to team scales and we can accomplish more.
Text, and same with an API.
And the same thing with an API.
Orange screen with text, complex versus complicated.
So far I've been trying to get across the important difference between this complex and complicated domains. But now let's take a closer look, let's go a little farther and take a closer look at the complexity in our business context so that we get a better idea whether or not the SLOs that we create are actually well formed and achieve the goal of reducing complexity.
Orange screen with text, Wordly maps.
To get at the fine-grained structure of complexity in the business context, we'll use Wordly maps.
Graph with x-axis marked evolution, y-axis marked value chain. Evolution progresses from genesis to custom built, to product plus rental, to commodity plus utility. Value chain progresses from invisible to visible. The word customer connects to 4 points on the map on the high end of the visible range: online image manipulation, online photo storage, website, and print.
This is a Wordly map.
Online image manipulation is custom built, highly visible. Online photo storage is more custom built, slightly less highly visible. Platform is product plus rental, mid-level visible. Data center is product plus rental, low-level visible. Print is product plus rental, highly visible. Website is product plus rental, less highly visible. CRM is product plus rental, mid-level visible. Compute is product plus rental, low-level visible. Power as commodity plus utility, low-level visible.
In particular, this is an example map for an online photo service from 2005.
A red circle appears around the word customer, plus anchor, user needs. A red arrow marked plus position, relative to anchor, parallels the y-axis. A red arrow marked plus movement, evolution, parallels the x-axis. The point marked data center is colored red, and next to it appears text, plus components. A table with 3 columns appears in the top right. The first column reads basic map. The second has 6 cells that read visual, context, position, anchor, movement, components. Next to the second, the third column reads yes for each of the 6 elements.
So let's take a moment to familiarize ourselves with the various concepts in the wordly map so that you'll be able to get the gist of the maps I show next. The map is visual and context specific. In other words, it is unique in the line to that line of business containing the components that influence it at that moment in time. So again, online photo service for a specific thing in 2005. The map has an anchor, which is the customer. The position of components in the map are shown relative to that customer on a value chain represented by the vertical axis. Each component needs the component below it. The closer to the customer and the higher up on the vertical axis, the more visible the component is to the customer. Farther down on the vertical axis, the less visible the component is to the customer. For example, the customer cares about online photos, which requires storage, which requires a data center and power. And the data center and power are going to be hardly visible to the customer. The components of the map also have a stage of evolution, which is the horizontal axis. So on the left, Genesis represents the unique, the very rare, the uncertain, the constantly changing, and the newly discovered. Our focus here is on exploration. Custom built represents the very uncommon and that which we still are learning about. It is individually made and tailored for a specific environment. It is bespoke. It frequently changes. It is an artisan skill, and you wouldn't expect to see 2 of these that are the same. Our focus here is on learning and our craft. Next is product, including rental, and this represents increasingly common. The manufactured through a repeatable process. The more defined, the better understood. Change becomes slower here. And while there exists differentiation, particularly in the early stages, there is increasing stability and sameness. You will often see many of the same product. Our focus is here on refining and improving. And then we have commodity, including utility, and this represents scale and volume operations of production. The highly standardized, the defined, the fixed, and the undifferentiated. The fit for a specific known purpose and repetition. Repetition and more repetition. Our focus here is on the ruthless removal of deviation, on industrialization, and operational efficiency. With time, we become habituated to the act. It is increasingly less visible, and we often forget that it's even there, like a power and a power plug. And the components continuously move from left to right in an evolution axis driven by the market forces.
On the left side of the map, from the top down, read uncharted, chaotic, uncertain, unpredictable, changing, different, exciting, future worth, unusual, rare, poorly understood, experimentation, differential, competitive advantage. On the right side, from the top down, read industrialized, ordered, known, measured, stable, standard, oblivious, low margin, essential, ubiquitous, defined, volume operations, operational efficiency, cost of doing business. A dotted red line crosses the map from a point marked past, through a point marked platform, to a point marked future. The text, plus competition, appears above the dotted line.
So that's a map. There's a lot to worldly mapping that we aren't going to begin cover here, but one aspect I want to highlight is this aspect of movement. The fact that components change as they evolve towards commodity and utility. So take a note here of the characteristics on the genesis side of the evolution axis and compare them to the characteristics on the commodity side. On the left, we have uncertain, unpredictable, poorly understood, competitive advantage. On the right side, we have ordered, known, stable, obvious, operational efficiency, cost of doing business.
On the left of the map appears the word complex, on the right, the word complicated.
So if we view these through our previous framing, we can see that components go from being thought of as complex to eventually being thought of as complicated.
The map appears faded gray beneath two groups of 5 people each. The group on the left has lines connecting each person and trailing off in all directions. The group on the right is surrounded by a dashed line circle, with lines connecting each of the 5 to the others. A red dashed arrow marked API, SLO, points from the group on the left to the one on the right.
If we go back now to the idea that creating APIs and SLOs contains complexity in a complicated container and allows us to scale, we see that those same techniques help us provide stability and enable us to be viewed as complicated by the users of our APIs and SLOs. And these techniques allow us to shift our service and components closer and closer towards commodity utility. It's like, okay, fine, and so what? Like, why does that matter?
A graph marked evolution on the x-axis and value chain on the y-axis appears. 3 points show nearest to Genesis on the x-axis, with television high on the y-axis, visibility, computing in the mid-range, and radio on the lowest. Lines connect each of the 3 to a point on the right marked electricity, low visibility, in the commodity plus utility segment of the x-axis. A red dashed line, marked plus worth, points to the right from television. Another red dashed line, marked plus competition, points to the right from a red dot marked Parthian battery. The second red dot is at low visibility, nearest to Genesis, and the line leads to the point marked electricity. Title: Climatic Pattern. Higher order systems create new sources of worth.
And in the business context, this is where the business context becomes relevant, is shifting towards commodity means that we will start getting efficiencies brought on by commodity and utility. It enables innovation and creation of new sources of worth on top of those commodities and utilities.
On the right side of the screen appears text, constraints, fixed at time scale under consideration.
A shift towards commodities stabilizes the system, it freezes the constraints, and this in turn allows others to generate new complex things on top of stable, complicated commodities and utilities. And in turn, those complex things become stable over time.
On the left side of the map, from bottom to top, are Parthian battery at low visibility, Genesis, Z3 plus new, SDC, and an unmarked point. On the right side of the map, from bottom to top, are electricity at low visibility, commodity plus utility, computing, databases, intelligent agents at high visibility, product plus rental. A black arrow marked line of the present connects the points on the right-hand side. The end of the arrow reads toward user need.
And we invent new complex things on top of those, and so on and so forth, and thus allowing us to survive in the business environment while continuing to playing the infinite game.
Red dashed lines zigzag upwards from the point marked Parthian battery to electricity, to Z3 plus new, to computing, to SDC, to databases, to the unmarked point, to intelligent agents. The lowest line reads plus competition, the point nearest electricity reads plus efficiency, and the second line from the bottom reads plus componentization. Title: Climatic Pattern. Efficiency enables innovation.
So before we said that this is why SLOs are useful.
Blue screen with text. SLO is a complicated container that encapsulates complexity so that at organizational scale we can accomplish more.
But now you hopefully have a better idea of what this nebulous accomplish more means.
Text. SLO is a complicated container that encapsulates complexity so that at organizational scale we can generate new complex sources of worth.
It implies that commoditization allows us to generate new complex sources of worth. And that's sort of why we're all here, and that's how we can keep playing the infinite game. And that's all I got, and I can take some questions and answer, and I guess everybody else can too.